Good morning, everyone. We're going to pick back up here in Chapter 5. We should be finishing Chapter 5 today, then Wednesday moving on to Chapter 6. So I'll have a new set of lecture slides up for Wednesday's lecture into next week. Into later this week, Thursday, Friday, no class for fall break. That's for obviously all your classes, so looking forward to that, I'm sure. The recitations still meet this week as scheduled. Recitation basically meets every week of the semester, either to take an exam or to have an activity. If you look ahead to the very last week of recitation, there's a ungraded activity that's going to be a review activity. I'll send this out later, but that's going to be a chance for anybody to make up a missed recitation session. Just to kind of talk about recitation for a moment, you get one drop out of the required attendance days for recitation. So you can miss recitation once without a penalty. If you miss 2 or more times, then you start to lose points, but we'll give everybody a chance to earn back, a second miss with attending that very last recitation, just to put that on your radar. So if you look at the recitation schedule, basically attending every week, with the exception of the last week being optional if you've attended enough recitations to have a 100% score. Okay, so let's talk about enthalpies of formation. The idea of enthalpies of formation, let's start with the simple idea that if you had a reaction, let's say 2A goes to B, that in order to calculate delta H of the reaction, what we would want to do, the ideal problem to solve for this would be to know the enthalpy of B, so to somehow take the enthalpy of B and then subtract 2 times the enthalpy of A. But the problem is enthalpies are hard to directly measure. It's hard just to measure the enthalpy of a substance. And so instead what we'll see is that we kind of replace the idea of trying to understand or know what the absolute enthalpy is of a given substance and replace this with something that we call the enthalpy of formation. And so we can also say that the delta H of reaction would be equal to the standard enthalpy of formation of B and then minus 2 times the standard enthalpy of formation of A. Where these standard enthalpies of formations, these delta HFs, are more easy for us to determine in the laboratory, and they're going to be the values that we tabulate. But what we're going to see is they kind of replace the idea of the absolute enthalpies of these substances and give us a way of just tabulating values that we can then take the difference of between the products and the reactants. And so they're kind of a replacement for the idea of taking the enthalpy of the products minus the enthalpy of the reactants. Only issue, though, we got to account for the stoichiometry in the reaction. And so 2A, so I have to, have 2 times A here, no matter which system I'm kind of thinking of. And so it's just this way. Here is harder for us to measure. So we're going to see that this is just a more common way that we go about trying to solve for and determine the enthalpies of reaction from enthalpies of formation. But now let's more carefully talk about what enthalpies of formation are. So enthalpies of formation are where we're talking about the enthalpy it takes to form a compound. And when we write a formation reaction, we're going to be careful just to write the formation reaction to produce 1 mole of a compound or a substance. And so I have 1 mole on the product side, and then I can leave the balancing with fractions in this reaction. It's okay in this reaction to have fractions if we need to have them. And so when we go to form a product from its elements in their most stable states at room temperature, it's going to require us to think just a little bit about, what is the most stable form of oxygen? I think that one's pretty easy. We know it's O2 gas. So the formation reaction of O2 gas is from O2 gas, and that's pretty easy, right? That forming something from itself can't have an enthalpy difference. And so elements in their standard state are going to be defined to have a precise 0 standard enthalpy of formation. On the very next slide, I'll review kind of what that most standard state is for most of our elements, but we can sort of think at the moment, before we see that slide, that it's going to be kind of like for our metals, just a metal solid. And there's one metal that's not a solid, that's mercury, which is a liquid. And then we have our non-metallic elements, which some of them are diatomic, like H2, N2O2, F2, Cl2, Br2, I2. So some of them are diatomics. The next slide will review those for us. But then some of those are maybe elements that we don't encounter that often. Like for example, like selenium's not something we tend to work with too much. So some of the elements, we're not going to tell you the standard form of it because they're not so common that we don't work with them that much. So we're going to focus on the more common elements and their standard states. Carbon's an interesting one. The most stable state of carbon, let's actually start with this next, is graphite. So if we look up the delta HF, and by look up, I mean, you can look up a lot of different substances in the back of the textbook or in the end matter of the book. There's an appendix that lists a bunch of delta HF values. There's also other resources like the CRC lists a bunch of these. The NIST chemistry web book lists a bunch of values as well. So there's other online resources that you can use to look up standard enthalpies of formation. But carbon graphite is the one that has a 0 enthalpy of formation. So it's the most stable form of carbon. So the formation of carbon graphite would be from itself. So that's the form of carbon that's most stable is graphite. And then if you actually look up the diamond form of carbon, towards the end of the class, we'll take a look at the structural difference between diamond and graphite. The main difference between graphite and diamond is graphite has 2-dimensional sheets of carbon atoms, and diamond's 3-dimensional arrays of carbon atoms. And so the 3-dimensional array gives you a stronger form. Graphite has 2-dimensional plates that slide off each other. That's why they're good for pencils. And so we make carbon diamond from graphite. And then the delta HF here is slightly positive. Or it's actually 1.88 kilojoules. It's actually just barely higher in energy and enthalpy than graphite. So diamond is slightly less stable than graphite. Now that doesn't mean you can easily turn graphite into diamond. If you could, you would have lots of diamond. It is possible if you pressurize graphite, you can turn it into diamond. So you can make diamonds in the lab. They're not going to look as brilliant. They're going to have more imperfections. They're useful for like saw blades and different mechanical purposes that just need something sharper, but not necessarily something that looks, exquisite that you would spend a lot of money on. But anyway, so diamond is slightly more stable than carbon. Now, if you're not sure, you can always look up in something like an appendix, go to that back matter, and try to find what is the form of an element that has a 0 delta HF. That's going to be the most stable form. And so this tells us that graphite's the most stable form. Now, getting back to the next molecule down, this is O3 is called ozone. There's an ozone layer. It's useful. It helps block out UV rays from the sun, but it's a lesser stable form of oxygen. We know this because if it was more stable, we'd probably be breathing it in, would have talked about it more, but O2 is more stable. The formation reaction would come from O2 gas, the most stable form of oxygen. Here, 3 halves is fine to balance out the O2s. So that gives me 3 oxygen atoms on both sides of the equation. And so then if you notice the delta HF is positive, meaning it takes energy from oxygen to create ozone. And so ozone is a lesser stable form of oxygen. And so ozone is not going to predominate in a sample of oxygen at room temperature. So O2 is the more stable form. It also takes energy to break that bond. Bond enthalpies is the next topic in chapter 5, but it's going to take energy to break a chemical bond. And so O atoms are even higher in energy here. So having O atoms would require energy by O2 to absorb it. Or another thought would be if you had 2 O atoms, they would rather exist as O2 than as O atoms or as O3. Okay, then if we look at CO2 and say, can we write the formation reaction for CO2? Would just require us to think, well, what's the most stable form of carbon? That's carbon. A lot of times you'll see us just write solid. We won't necessarily always specify graphite, but a lot of times we'll just have carbon solid is the form of carbon. We might be thinking, well, it's going to look like graphite in terms of its form. And then our O2 is going to be the form of oxygen. So carbon solid plus O2 balances out the CO2. Now, most compounds will have a negative delta HF, though they don't have to have a negative delta HF. Negative delta HF is helping us see that CO2 is more stable than the elements of carbon and oxygen, which is generally going to be the case. Not always. There are a few compounds that are stable that actually have a positive delta HF, but most compounds are more stable than their elements. It's one reason why they exist in their compound form as opposed to decomposing into their elements. If we want to write the formation reaction for H2 gas versus H2 liquid, it doesn't really matter. They both have the same formation reactions. I have H2 gas plus a half O2 gas, and then both of those work to lead to water, gas, or liquid. And so if the physical state of the product changes, we don't have to change anything with the reactant. So when I'm producing water liquid, it's still coming from the gaseous form of H2 and O2 because that's their most stable form. So you're looking at just hydrogen. What's its most stable form? Hydrogen's a gas at room temperature. Oxygen's a gas at room temperature. They both exist as diatomic molecules. And so just a half O2 to balance here. And so then if you notice, they have a difference of enthalpy of formation. If we were trying to calculate the enthalpy of reaction for, say, water liquid to water gas, so we talked about this phase change last time, but if we're boiling water, do we remember if that's exo or endothermic? Just from the thought of, does liquid water have to absorb heat to boil or give heat off to boil? It has to absorb heat to boil. We have to add heat to that in order for it to take place. And so the delta HF process would be the delta HF of water. And so the delta HF of water, these should all be per mole here. I don't know why I left off the per mole. But the delta HF of the product gaseous water minus 241.82. So delta H of the reaction should be the negative 241.82 for the product, and then minus the reactant. So kJs, I'm multiplying by 1 mole. So like I have 1 mole of water on the product side, so 1 mole kJs per mole. So that's where the per mole goes here when I start writing out the delta H of the reaction. And then minus the water as a liquid, which is minus 285.83. So if we do that difference, it's about 44. So 241.82 negative minus negative 285.83 gives me plus 43.48. So if we recall, we predicted this would be endothermic. Here we can look up the delta HF values and precisely calculate that delta H of reaction. And so that's the utility of delta H's, is to be able to use them to calculate delta H's of reaction, so we can have, you know, a random reaction of reactants and products balanced out, and we can then solve for the delta H of the reaction. Let's take a look at one more delta H enthalpy of formation reaction for CH4. So carbon solid for carbon, and then plus the 2H2 gas to balance out for 4 hydrogens. And so it's not carbon gas plus 4 H atoms, or it's not carbon solid plus 4 H atoms. It's specifically the enthalpy difference between carbon graphite and 2 molecules of H2, or more specifically 1 mole of carbon solid plus 2 moles of H2 forming 1 mole of CH4 would have a delta HF of 74.8 kJs per mole. The whole idea of having the 1 mole of product is so that you can sort of see that the delta H of each of these reactions that we've written would just be equal to the kJs per mole times 1 mole. So the delta H of this reaction, the last one I wrote, was 74.8 kJs. Think about how the delta H of reaction takes into account the number of moles. So 74.8 kJs per mole of CH4, there's 1 mole of CH4, so 74.8 kJs. And then the delta H of the reactants are 0. So the products minus reactants is the products delta HF minus 0. And so that's how the delta HF reactions work, is they're showing you the product being formed from its elements, or the elements have a 0 delta HF. So if we go back to the water, liquid, and gas, their delta H's of reaction would be minus 285.83 kJs versus minus 241.82 kJs. And the CO2 being minus 393.5 kJs, and then plus 142.3 kJs for the ozone. So just multiplying by 1 mole. And so that's the idea of delta HFs. If you form 1 mole of the substance, then the delta H of that reaction is sort of defining the kJs per mole, the enthalpy of formation of that compound. So the standard enthalpy of formation is forming the compound as a product from its elements in their standard states at room temperature, so that we know the delta H of the reaction is the product's delta HF minus 0. And as I mentioned, I would show you, just to go over and review, like what are the most common physical states that are defined to have this 0 delta HF. And so we have a bunch of gaseous elements, so that would be H2 gas, N2 gas, O2 gas, F2 and Cl2 gas. You don't see Br2 and I2 because they're not gases, it turns out. We'll talk about those in a minute. But then we have our noble gases. So our noble gases are gases at room temperature, just as monoatomic gases. So for like neon, be neon gas. But for H2, it's H2 gas. Now we have two liquid elements, Br2 and Hg liquid, and so we'd have Br2 liquid as the most common form of bromine, and then Hg liquid. And then for solids, most of our elements are solids at room temperature because most of our elements are metals, and most metals other than mercury are solids. So we'd have Na solid, calcium solid, iron solid. And so those are sort of the key metallic solids. We also have some metalloids and non-metallic solids like carbon graphite that we mentioned earlier. The white form of phosphorus turns out to be the 0 delta HF, but rarely would we ever use phosphorus in an example on an exam. Sulfur is rhombic form of sulfur, and then I2 is also a solid. Now, like phosphorus, sulfur, rarely used in examples, but they're relatively common elements. I thought I should tell you and show you their physical forms that have a 0 delta HF. And so let's go through a couple examples of elements that would not have a 0 delta HF by definition. So H atom, the hydrogen atom, if you think of it this way, think of this reaction here, H2 gas, and really this reaction is coming next in our notes in section 5.8, that this reaction here has to require energy because the H2 bond is stable. It's going to definitely require energy to break that bond. And so this reaction here has a positive delta H. And hopefully we can see that. We'll see in a moment once we see bond enthalpies for sure, we'll be able to predict that this should have an endothermic nature to the reaction. Energy has to be absorbed to break a stable chemical bond. And so that's not going to have a delta H of 0 for the H atom. If you have the O atom, again, the same thing. If you break the bond in O2, that has to require the absorption of energy to go to 2 O atoms. So that has to be an endothermic reaction as well. Other forms of things like phosphorus or sodium gas versus calcium gas, having the gaseous atom instead of the solid, it has to require energy for a metal solid to liquefy and then to boil. Probably not likely transitions. Like I don't think we're gonna take a block of sodium and boil it and then vaporize it. That sounds kind of crazy to do, but if we did so, that would require a lot of energy to be absorbed in the process. Therefore, no delta HFs for sodium gas or calcium gas. And then also ionic forms don't have 0 delta HF. So if you have like the ion of iron, that doesn't have a 0 delta HF. If you have a different physical form of a gaseous element like N2 liquid, that doesn't have a 0 delta HF either. So only the elements in their precise, most stable form are defined to have 0 delta HFs. That's just because in the formation reaction, you'd have the element on the product side and then the exact same form of it on the reactant side. So therefore, we'd have to have a 0 delta H. Okay, and so then the utility here is, as we were getting at, is to be able to use these delta H's to calculate delta H's of reaction. So a delta H of reaction is found by summing the product's delta HFs. N here just means if you're imagining you're taking M times A goes to N times B, that for the products you have to take into account the number of moles. So accounting for the stoichiometry in the reaction, summing up the products, delta H's of formation, and then subtracting those delta H's summed up for the reactants. And of course, we have to take into account the reactant stoichiometry as well. So to give us an idea of how to do this process, let's take a look at this reaction here, the combustion of methane. So we balance it out with O2 to form CO2 and water, where water is a gas. And so we can look these up in appendix or a textbook. They happen to be on the previous slides as well. And so I might have to flip back. But I think and you guys can let me know if I'm right or wrong on some of these, that CH4 was at minus 74.8 kJs per mole. CO2, I think, was minus 393.5 kJs per mole. And water as a gas, was that one minus 241.82? And so then the delta H of reaction, I think this is pretty straightforward, right? Because what we want to do is just take the 1 mole of CO2 as our first product. So we're just taking the sum of the products first. And the delta is just final minus initial. So if we think of it that way, it's just the final form minus the initial. So I think the 1 mole of CO2 times negative 393.5 kJs per mole. So that's where the mole is canceling out. If you do recall delta H's of reaction, are usually just units of kJs, just units of energy, not necessarily per mole. And so then we sum, so that's why we have a plus sign here, is we're summing up the products. And so then we take the next product, water, 2 moles of water times the negative 241.82. Again, that's where the mole unit is disappearing to. And then we're subtracting final minus the initial. So then this is the sum of the products, and then we're subtracting the reactants. I have 1 mole for CO2 times 74.8 kJs per mole. Now, I didn't write anything in for O2, and that's because I was imagining the delta HF here is defined to be 0. I didn't have to look it up. I could double check or remind myself that that's the elemental form or the most stable form of oxygen. If I want to write this, I can, but it's not really all that necessary to write this step in where it's 2 moles times 0. But 2 moles times 0 for O2, just to show that we can think about O2 and just remind ourselves that that's going to be the state that's equal to 0. And I can certainly tell you that when we give a test and give you a question on the delta H, it's very common for us to give you a reaction that has at least 1 element and 1 spot of the reaction, and we give you the delta H's of all the things except for the thing that's 0. And then one of the choices is often there's not enough information to answer this question. And the only reason you would think that answer is reasonable is if you think you need to know the delta HF of the element in its standard state. And if we do this, we choose really simple examples for the elements like hydrogen, O2, N2, like a metal solid, a really easy example, not those goofy phosphorus or sulfurs that might be a little bit tricky to remember. But anyways, solving this problem here, taking the sum of the reactants. Now the only thing is there's a bunch of minus signs. I just try to be really methodical here. I do 393.5 negative, and I really do plus, and then 2 times the negative 241.82, because I find that if I try to think too much about the sign of the number, that I usually screw it up. So if I'm just very methodical of just taking the negative number plus the other negative number times 2, I usually don't make a mistake that way. And then I do minus the 74.8 negative. And so I'm just being usually very methodical just to try to do the math on the paper and not think too much so that I can just let the calculator do the hard work for me. But I get the delta H of this reaction is minus 802.34, call it minus 802.3 kJs. And again, not kJs per mole, all the moles had canceled out. And so that's how we can use delta H's, and this is really the utility of delta H's, so that we can use them to calculate delta H's of reactions, so we can just look them up as needed in a variety of resources. Now let's take note of something else. Remember how we said if you double the coefficients, if we made this reaction 2CH4 plus 4O2 goes to 2CO2 plus 4H2O. Because water can be multiple states, I'll write water as a gas just to make sure we're seeing that we're keeping the coefficient of water and the form of water the same. If I double the coefficients, what should I do to delta H? I should double it according to what we saw like in Hess's law and what we saw with the first law of thermodynamics. So this delta H should be approximately this delta H times 2. So that'd be minus 1604.7 kJs. But what I just want us to think about for a minute is how if you just double the CO2 and quadruple the water and subtract 2 times the CH4, that you get 1604 negative. So like the reason why you double the coefficients is because you're doubling the magnitude of the sum of the delta H of the products, and you're doubling the magnitude of the delta H of the reactant, so therefore you're doubling the difference. And so it just comes from the math. It just comes from if you want to plug a 2 mole in here, plug a 4 mole in here, and plug a 2 mole in here, and just see what the difference is, and then it's 1604 kJs. And so the kJs for a reaction, we say a reaction like the first one that was minus 802.3, when we conclude that's the delta H of the reaction, we're understanding or we're assuming that the coefficients in the reaction are all moles. So we're assuming that this is the delta H precisely for 1 mole of CH4 reacting with 2 moles of oxygen to form 1 mole of CO2 and 2 moles of water. So the coefficients are assumed to be moles in our balanced reaction that relates to the delta H. So I can't give you a delta H of a reaction without showing you the reaction. You have to be able to see a reaction so you can see what the coefficients are in order to understand and relate the delta H to it. Okay, so how does this work? I wanted to show just kind of like, well, how is it that each of the formation reactions, which is a reaction in and of itself, how is it that I can take a series of these delta H's and then sum them up accordingly to determine the delta H of formation? And so let's think for a minute about how we had talked that CO2's formation reaction was carbon plus O2 goes to CO2. So that was our delta H of formation reaction of CO2. The delta H of formation of water is the second reaction. I doubled those coefficients because we have 2 waters in our product state. If you remember the idea of Hess's law, if I can sum reactions up, then I would cancel out the things on the reactant and product side, and then I would sum up the individual delta H's. Well, if I double the coefficient for water, I have to double multiply the delta HF times 2 moles instead of just times 1 mole for CO2. And so that's CO2's delta HF plus water's delta HF so far times 2. And then why do we flip or go negative the reactants? Well, to get CH4, instead of on the product side, but onto the reactant side, I need to flip the delta HF reaction. So if we flip a reaction, you flip the sign. And so this is why we had the sum of the products and then minus the reactants, because we're just flipping the reactant in terms of its delta HF reaction. And then if you notice here, because the reaction's balanced, the products come from the same set of elements as the reactants do. And so the reactants of the elements are canceling themselves out. And so that the net difference here, the reaction CH4 plus 2O2 goes to CO2 plus 2 water. And then that simplifies down to being minus 8O2 like we saw earlier, kJs. And so the reason why delta HFs work is just, it's an example of Hess's law. So if we're defining all substances relative to their elements, and then any reaction we consider is legally balanced, if we have a perfectly balanced reaction, then the reactants come from the same set of elements as the reactants. And then it's all about just taking the sum of the products minus the reactants and seeing here how and why this works. Okay, so one of the things from, like if we were able to complete the bomb calorimetry problem, which we could do, it just takes a fair bit of time. If you remember, there's this one problem, I can't remember if it was last lecture or the lecture before that, but if we wanted to use bomb calorimetry to understand how we determine enthalpies of combustion, the only real utility there is kind of seeing that that's the basic experiment that we do to determine delta HF values. So if you ever go like in the appendix, you have all those delta HFs of a bunch of different substances. How did we come to know those values? They're really through bomb calorimetry examples. Like what you would do with a bomb calorimeter is you would blow up hydrogen, figure out how much hydrogen you put in a calorimeter, and then see how much heat it gives off, and that's how you work out the delta H of combustion of H2. That's how you ultimately determine the enthalpy of formation of water. You do the same thing for carbon graphite. That's how you determine the delta HF of CO2. And then you do this for a bunch of other organic compounds. That's how you determine their delta HFs. So we didn't see the experiment. We're not going to put it on the test because we rarely test that concept. I don't want to waste our time too much on examples that we're not going to see or aren't important for our examinations. But if you look at the thousands or millions of delta HF values that are known, they almost all come from bomb calorimetry experiments. And so if we had determined from a bomb calorimeter example, let's say, that the enthalpy of combustion of C7H18, let's say it was minus 4816 kJs per mole. And so heat of combustion just says that when this compound here combusts with excess oxygen, that it gives off 4816 kJs per mole. So it's losing a lot of energy. If you recall, combustion reactions take place with a flame or a combustion, so they have a really big negative delta HF. We see that here, negative 4816 kJs per mole. And so I have 1 mole of the substance here, so my delta H of this reaction should be 4816 negative kJs just times 1 mole. So I have just 1 mole here, so I just multiply by 1 mole. So the delta H of the reaction should be minus 4816 kJs. And so the way I could take my delta HF and determine my delta HF of the reactant C7H16 is to look at this reaction and realize I already know CO2 and water because we gave you those values previously. If you remember, the delta HF of CO2 was minus 393.5 kJs per mole, and liquid water was the minus 285.83 kJs per mole value. So we know those delta HFs. And I know the delta H of the reaction. The only delta HF I don't know in this problem is the C7H16. And so can we calculate the enthalpy of formation of heptane using this delta H of reaction? Okay. And we even have CO2 slightly more precisely given to us here as minus 393.51. Okay, so the way I would work this problem out is the delta H of this reaction, which we already know the delta H of the reaction, but the delta H of the reaction would be the sum of the products of this reaction's enthalpies of formation minus the reactants. So I'd have 7 times CO2. Let me use the more precise number, minus 393.51 kJs per mole. It's 7 moles, that's where the mole's going. Then we have to sum up the product, so I add 8 times 8 moles of water times negative 285.83 kJs per mole. So that's the sum of the products, delta HFs. And then I have to subtract 1 mole times the delta HF of C7H16. And then oxygen's still 0, so I'm going to ignore oxygen. So that's the complete sum of the reactants, delta HFs. And all this is equal to minus 4816 kJs. So let me work out this math here. So 7 times 393.51 negative plus 8 times 285.83 negative So I get minus 5,000. So all of this works out here to be minus 5,041.21 kJs. All of that is still equal to minus 4816 kJs. So all I need to do here is add 5,041.21 to both sides. To cancel that out. So that works out to be plus 225 kJs is equal to negative 1 mole times the delta H is C7H16. And this minus 1 mole, the minus sign is only coming from the minus the reactants. It's the sum of the products minus the reactants. There's 1 mole of the one reactant that has a non-zero delta HF. So it's minus 1 mole times the delta HF is C7H16. So divide by negative 1 mole. So if I divide by negative 1 mole, I get negative 225 kJs per mole. And that is my delta HF of C7H16. So there's 2, yes, let me take your question first.
Okay, first, moles for the last problem, the positive 225, was it kJs per mole or just K?
Just kJs, because we have minus 4816 kJs, and then this value here is just kJs. So once we have the kJs per mole from the delta HF times the number of moles, the moles go away.
In addition to that, in the first equation of enthalpy of reaction, is that a negative 476 kilojoules? Or what number was that supposed to be?
This one here?
Yes.
Oh, that's this number here. So it should be 4816.
Okay, I just wanted to double check.
No, that's fine. I know my handwriting stinks, and I forever apologize to everyone in the room. But yeah, so 4816 kJs, and so, yeah. And so we had plus 225, and then I divided by negative 1 mole to get negative 225 kJs per mole. Now again, it's not always going to be the case that a delta HF is negative, but the delta HF here is negative, showing that the compound is more stable in the form of C7H16 than it is separated elements. Okay, so the two basic ways you can see a standard enthalpy of formation problem is to have a reaction either given to you or where you balance it out yourself, and then you take the sum of the products minus the reactants if we give you all the delta HFs, with maybe the exception of an element that we expect you to know is 0. Then the other approach could be we give you a reaction or a reaction that you can balance out, and we give you the delta H of that reaction, and then all but one of the delta HFs of the reactants or products, and then you can solve for the one that's unknown. Okay, so the last section in the book is on bond enthalpies. And so bond enthalpies are generally and always going to be positive. It takes energy to break bonds. So this is the idea of bond enthalpy is how much energy does it take to break a chemical bond. So bond enthalpy is positive because energy is required to break bonds because there's some reason why the bond existed. There's some greater stability in the bond forming than it having been broken. And so the greater the bond enthalpy, then we would say that means we have a stronger bond. So if you look at the single bonds are up at the top, and also let's try to make sure we understand some expectations. If I show you a formula, you can't necessarily determine yet if it's a single bond, double bond, or triple bond. I don't expect to give you a formula like N2 and expect you to know N2 has a triple bond yet. We don't get into bonding models until like chapter 8 and into chapter 9. So I don't expect you to know and predict the bond types yet. But if we show you a bond, so you can see schematically, like if I show you N2 looks like this, and that's how we're saying that's what we call a triple bond. And so the triple bond of N2 is down here. That's 941. And the unit for all these bonds is kJs per mole. So it's 941 kJs per mole. If I look up the comparable NN single bond, which is right here, if we have a single bond between the nitrogen atoms, it's only 163 kJs per mole. So the greater the number, the stronger the bond. So the NN triple bond, really strong. That's why N2 is so stable. That's why our atmosphere contains nitrogen in the form of N2 molecules, because it has that strong bond that's going to be hard to break, as opposed to something that only had a single bond. If a nitrogen-nitrogen single bond exists in a molecule, really easy to break that and form something else as a result. And so the stronger the bond, the greater the bond enthalpy. And we'll see as we get into chapters 8 and 9 too, that single bonds are always going to be weaker than double bonds, which are weaker than triples. Triple bonds are the strongest, double in the middle, single are the weakest. And then energy is released if we can form a bond. So if I can take two atoms, let's say I take two H atoms, we form H2 gas. So if I take atom fragments and form a bond out of them, then that should release energy. And so this reaction here should have a negative delta H, implying heat's given off in the process if we take atoms and form the bond from it. So break a bond, energy is required. Obviously, if you flip the reaction and form the bond from fragments, then enthalpy should be released in that process. And the utility here is being able to use bond enthalpies to approximate delta H's of reaction. But now this is the only case where this little symbol here is really applicable in a problem in this chapter, where this is an approximation technique, because bond enthalpies, we average them out for a type of bond, and it's not always going to be exactly the bond enthalpy for any one of those types of bonds. And so we can get an approximation of a bond enthalpy using this approach, and not necessarily and always the exact and precise and exact delta H of reaction. Now, this lets me kind of then take a step back and say, well, what about enthalpies of formation? Well, enthalpy of formation, you look it up for a specific molecule and compound that you know precisely. And so enthalpies of formation give us exact calculations of delta H's of reaction. If you look at calorimetry, those are giving us, assuming good data in the lab, those should be giving us, exact calculations of delta H's of reaction. Here, this is the only case we're getting an approximation. So also, let's go back to Hess's law. Hess's law is an exact calculation. It's just using the first law of thermodynamics. So Hess's law is giving us an exact calculation, not an approximation. This is the only example in this chapter where we're really getting a true approximation from the process. But then let's also take a look here that it turns out that we take the sum of the broken bonds minus the sum of the formed bonds. And the broken bonds are the ones in the reactants. So these are the broken bonds in the reactants minus the formed bonds in the products. So notice that this kind of goes counter to the way you would calculate most deltas. Most deltas you think is being the final minus the initial. This one here is going initial minus the final, but we'll see why ends up being a result of how Hess's law applies to this example. So this example here, we're breaking the bonds in the reactants and subtracting the energy it takes to form the bonds and the products. Let's look at an example to try to figure out why that's the case. And so the example, first one we look at here is the methane combustion reaction. And so CH4 plus 2O2 goes to CO2 plus water. Now, another thing that we don't necessarily specify in that chart is the physical state. To be fair, the physical state of all those atoms is assumed to be gases. So if we had the gas phase reaction where we're forming CH4 plus O2, forming CO2 and water as a gas, that will be our best approximation here. If you remember, water can be a liquid, but we're not going to get a good approximation if we're assuming water is a liquid here. So all that previous chart is giving us good ability to predict reactions more precisely when everything's a gas. But anyways, what we'd want to do to use our bond enthalpy process is to figure out how much heat does it take to break these bonds. So if I want to break apart carbon into 4 H atoms plus carbon, that takes energy. Energy is required to break those bonds. If we look up the CH bond strength in the previous chart, it's 413 kJs per mole. So I have 4 moles of that CH bond that I'm going to have to break. So that's going to take quite a bit of energy. I have to break the 2 moles of the O2 bond. The O2 bond strength is 495 kJs per mole. And there's 2 of those moles. Is CO2, I think it's 799 kJs on the previous page. Yep, it was 799 kJs per mole. So I got to form now the bonds on the reactant side. So let's think about how this works. The idea here, so if I'm breaking apart these O's into 4 O atoms, it takes energy to break those bonds. It takes energy to break the bonds in the CH4. Let's calculate that value first. So if I go 4 times 413 kJs per mole, that's 1652, plus 495 times the 2 moles of the O2 bonds, that's 2642 kJs per mole to break all these bonds. So to add these up here, 4 moles times 413 plus 495 times 2, that's plus 2642 kJs per mole. And so that's how much heat it takes just to turn these into their atom fragments. So we take our reactants, turn those into atoms, takes 2642 kJs. Then I take those atoms and I make new bonds. When I make new bonds, I release energy because I'm now forming bonds, but I'm forming new bonds. I'm now forming the CO bond, 799 kJs times 2 moles. And I'm forming 4 moles of the OH bond, which is 463, I think. Is anybody on the previous page on the OH bond? Is it 463? Okay, I can't believe I remember that. So I'm forming 4 moles, so I'm just counting here, 1, 2, 3, 4 moles of the OH bond and only 2 moles of the CO bond. So if I add those numbers up, if I add all these up here, what does that equal to? So it's 799 times 2 plus 463 times 4, that's 3450. So 3,450 kJs. Now, in the positive direction, 3450 is how much heat it would take to break the bond in CO2 and 2 waters into atom fragments. But we're not breaking the bonds here, we're forming the bonds. So if I have the atom fragments and I'm making the bonds, then that should be minus. It should be negative 3450. So it should be plus 2642 to break the bonds in the reactants, and I'm getting back 3450 when I make the bonds in the products. And let's do that math. 2642 minus 3450. I think it's 808. Yep, minus 808 kJs. It's a pretty good approximation, right? Because it was minus 802 was the number it should have been. I get minus 808 here with this approximation technique of using average bond enthalpies. Now, the idea of average enthalpies works like this. The CH bond in methane, like each of those bonds is slightly different from each other. As soon as we break one bond, we change the enthalpy of the remaining bonds. So that's what we mean by average. That to break all the bonds in methane on average to 413, we would specifically want to know the bond strength of those bonds in methane. If we had ethane, the CH bond strengths might be slightly different. If we had a different molecule, the CH bond strength isn't always going to be 413. And once we break one of the bonds in methane, the remaining bonds aren't always going to precisely be 413. So that's where the idea of approximation is coming in. But the idea of the sum of the products minus the reactants, this is just coming from Hess's law. So I think we have this shown here in the slide form where if you want to take the reactants and break their bonds, that takes energy. So breaking bonds is always an endothermic process, so big time endothermic, plus thousands of kJs per mole. Now let me also take a step back and say when methane burns, it doesn't really do this. We're not trying to say this is how methane burns. We're just trying to say and appreciate that if this is how much energy it takes to break the bonds on average, we should be able to then take the atoms and put them together in their new form. So we should be able to take the carbon plus the 4 H atoms plus the 4 O's and now change their form into CO2 and water and use their bond strengths to see how much energy we're getting back when we're making our new bonds. That's minus 3450. And so we're making, and this also allows us to see this like worked out with numbers, that we're forming stronger bonds. We start with bonds that are weaker because it takes less energy to break them, and we form bonds and end up being stronger because it would take more energy to break those bonds once they're formed. So it gives us this idea that when a reaction's exothermic, that the thermodynamic explanation of why it's exothermic is the bonds that we form are just stronger. Stronger bonds mean they're more stable. This almost comes back to the same idea as the oxidation reduction reaction, that we want to start with something that's more reactive, we want to start with something that's more reactive and produce something that's less reactive. We want to start with something that's less stable and produce something that's more stable. That's what we're doing here in this combustion reaction. We're starting with something with weaker bonds, we're leading to products that have stronger bonds. And we can work it out with numbers so we can see and support that with their relative bond strengths. And so then we put it together. Hess's law would say, well, our atom fragments cancel. And so in order to use Hess's law, we have to sum up the energy to break the bonds minus, because we have to flip the bond strength reaction, we have to flip the reaction to form the bonds of the products. And so the subtracting the reactants comes from the Hess's law need to flip that reaction to subtract the bond strengths of the products. Okay, and so that's the technique of bond enthalpies. I think there's one more example here on this topic of bond enthalpies. It comes back to kind of the opening reaction, which is water being formed from that violent combustion reaction of the hydrogen-oxygen balloon. Turns out, I don't know if I mentioned this, we're not allowed to blow things up in class for the time being. The fire department wants to sign off on some of our protocols before we start blowing things up and lighting fires in the room. So for the moment, I can't light things on fire for you. So hopefully we get that straightened out. So at some point in the semester, we can burn some more stuff and have some fun with lab demos. If you remember, we blew up that balloon with a huge kaboom. We saw all the energy being given off. We know that that's exothermic. We know that that's the idea of what it means to release energy. But why? Why does the formation of water from H2O2 lead to release in energy? So when a spark's given to a mixture of hydrogen and oxygen gas, and we see and we know that this violent combustion reaction takes place, why must that be the case? Well, we can think, does the reaction give off energy because the product's bonds are more stable than the reactant's bonds? That's sounding pretty good. Does the reaction give off energy because the reactant's bonds are more stable than the product's bonds? So are the reactant's bonds more stable than the product's bonds. That doesn't sound right because it's going to be hard to start with a bond that's really stable and produce a bond that's less stable and then have energy be given off. And so this here doesn't sound quite right, so B's not sounding right. C, the reaction absorbs energy, or the reaction doesn't absorb energy. We witness the release of energy through the violent combustion reaction, so the reaction's not leading to the absorption of energy. But the idea here, and we showed this even with the diagram, even on day one, we were talking about the potential energy landscape of hydrogen and oxygen being at the top of the potential energy well, and then water being at the bottom. And so in terms of an energy diagram, or an enthalpy diagram, H2NO2 at the top of the hill, water at the bottom of the hill. So we're leading to a compound that's more stable and has stronger bonds. So it's the difference in bond strengths that's leading to the idea of how a reaction can be exothermic or why a reaction is exothermic. So it's just relative bond strength. So if we're producing stronger bonds, we're producing more stable bonds, so we're going to have an exothermic reaction. And then if we have a reaction that's endothermic, we can imagine that the opposite must be true. So if we have a reaction that's taking place and we know it to be endothermic, we must know that the new bonds that we're forming must be weaker than the bonds we started with. But then you could probably say, well, why on earth would that reaction ever take place? Why would an endothermic reaction never spontaneously occur? Well, it turns out that there's that effect of the spontaneous or the entropy nature. So it comes back then to why a reaction can be spontaneous even though it's endothermic must be that the randomness is being increased. Randomness is what we call entropy, or is measured through entropy. We come back to that in chapter 19 and see that later. And so there's other driving forces than just the bond strengths. So you can have reactions that are spontaneous, that are allowed to take place, that go uphill in enthalpy, that produce weaker bonds, but there just must be some other thermodynamic force in play. That's the delta S, or the entropy. You'll learn about that later. Now, I thought for today, let's come back to, before we take off, why don't we do one or two more problems that kind of review. Calorimetry is probably the one topic in chapter 5 that everyone has the trickiest time with. This is coming from one of the daily quizzes. This specifically is, I was going to try to remember what daily quiz it was. It's, I don't know, maybe next time, I wonder if it's on the slide here. No, sometimes I put the slide. This is one of the daily quizzes. I think it's either from today's or tomorrow's or something. But anyway, so we have here a coffee cup calorimeter. Initially contains 150 grams of water at 25 degrees C. Cesium chloride's also 25 degrees C, dissolves in the water, and the final temperature of the solution goes up to 32.82 degrees C. What is the enthalpy of solution in kJs per mole of cesium chloride? And assume the specific heat of the solution is that of water. Now, think about what we mean by coffee cup calorimeter is just a container that's a good insulated cup. And so a good insulated cup's not going to lose heat to the surroundings. It's going to keep the heat inside the cup. So any of the heat that's released by the reaction goes into the solution. The main idea here is that the heat change of the reaction is going to be the negative of the heat change of the surroundings. That's very fundamental. So any heat lost or gained by a reaction goes to or comes from the surroundings. And then the surroundings here is the solution. So the surroundings of the reaction is the solution that it's taking place in. The heat of the reaction occurring in the calorimeter, I can calculate this by taking the negative M solution, CS solution, and then the delta T of the solution. I could also come back to an idea that should this reaction be exothermic or endothermic? If the solution went up in temperature, does that mean the reaction was exo or endo? Because if we get that right, we've got a 50-50 chance of getting the problem right. It's exothermic because the reaction releases heat. That heat goes into the solution temperature then goes up. So the reaction should be exothermic. So we should be at answers A or C. And then whether it's exo or endo has nothing to do with the negative sign. The negative sign is always there just from the relationship between the reaction and its surroundings. And so we have a negative M of the solution. The solution is the 150 plus 12.5 grams. So that's negative 162.5 grams. The specific heat of the solution, 4.184 joules per gram Kelvin. Delta T of the solution is 7.82 degrees C. The degree C and Kelvin cancel, that's fine. It's a delta T, so the delta T's in degree C equal to Kelvin. And so this gives me the Q of my reaction is 162.5 negative times 4.184 times 7.82. And I'm going to convert this to kJs, 1,000 joules per kJ. So dividing by 1,000, negative 5.32 kJs. Now that's the heat released into this calorimeter. That's the heat that's released specifically by 12.5 grams of cesium chloride. We want kJs per mole, so I just have to convert this number of grams to mole. And so we're told so we just need to then use the molar mass of cesium chloride, which is the mass of cesium, kind of running out of time here. But we just use the molar mass of cesium chloride to go grams to mole to wrap the problem up. It probably works out to be answer C. We'll probably take a quick look at this one to start class on Wednesday, then get into chapter 6. So there's one more example here on calorimetry. All right, guys, have a great day, and I'll see you on Wednesday.